question is, when I say sequencer, what I'm referring to is classic problems where we need a sequence of events to occur in a certain order. And those events may include waits or delays. They might include moving a motor for a certain amount of time or a certain distance. They often include extending or retracting pistons, any number of things, anything that has to happen in a specific order every single time. Do some people want to mention some of the subsystems that we've had on the robots that might fall into that problem category? How about you, Adam? Any thoughts on what subsystems might fall into that? So Adam says definitely the climber. So yeah, that's one for sure. And that's actually what I'm going to use for the examples today. Both the climber from this year, which the sequence was pretty straightforward, and the climber from last year, for which the sequence was definitely not nearly as straightforward. Any other mechanisms you might have on your minds? So a couple other examples are last year when after we score a game element in the rocket, the elevator would retract automatically. That automatic retraction required a sequencer, and it required different sequencers for each scoring position. Also, the 3-position PAL, although we didn't end up using it this year, there's actually a sequence, the PAL controller, to handle the 3 different locations, because the different pistons would have to extend or retract in a specified order in order to hit each of those positions. And then, and the other thing is, autonomous is really just one big sequencer of events. So the entire autonomous architecture is a sequencer, and that's one reason I want to cover sequencers first before we hit the autonomous architecture. Does anyone else have any last thoughts on sort of the types of problems we might tackle with a sequencer before we get into how to actually build one? Okay. So, does anyone have any thoughts on tools that we've seen so far that we might use in order to set up a sequence of events in LabVIEW? What about you, Alex? I see you're hiding underneath the Harold's login here.
What am I just joined.
I'm just joined. Are you unnamed?
Maybe.
Okay, well, now I know who you are. Perfect. Oh, look. Here. Now everyone knows who you are. So the question I just had was, what tools have we seen so far that would let us create a sequence of steps that execute in order in LabVIEW?
You have that, what's it called? In the structures thing, and it's like slashed, and then you add like little things.
So let me see if I can bring it up. So are you talking about the flat sequencer?
Yes.
Okay, so let's give that a shot. So the flat sequencer, I think, was introduced in one of the very first workshops, maybe even the very first one, allows you to set up a sequence. It allows you to create a certain number of steps by adding frames. And just make 3 here. And if you put actions into each of these, each of these frames, it's going to do each one of these actions. It's going to complete all the actions in one frame before it moves on to the next frame. So if we run this, you can see is that it'll go ahead and do this addition before it goes on and does these 2 additions in parallel, and it'll do the final addition. So that is a way to sequence events. Can anyone think of any potential issues with sequencing events this way? So what happens if one of the events that we're sequencing from the events is a wait? Like if I wanted to wait for a few seconds before proceeding on to the next frame. So I want to ask this one. Is typically in our code, is the sequencer the only thing that is running at a given point in time? Like if we're retracting the elevator, so it says input ask you this, if we're retracting the elevator, could the driver also be wanting to drive at that time? So Amelia said, yeah. So if we put a wait inside of our sequencer, we have to be really careful with how we do this, because the whole code is going to wait. Now, any piece of code that's not in a parallel loop is going to freeze and wait until that time period has elapsed. And because we want to make sure everything else is synchronized, we put all of our state controllers that are making all of the decisions for the robot in the same control loop, which has advantages. But the disadvantage is that if you then do a wait, you're going to block the driver from inputting any new drive commands while we're waiting for the elevator to retract or for any other wait that's occurring in the sequencer. And so what we want to do is avoid what we call blocking calls, blocking operations, things that you would do in the sequencer that would block anything else from executing the code until that event is complete. Does anyone have any questions on sort of, I guess, what the downsides are of putting a wait block in a flat sequence like this? Amelia asks, is there a way that you can make it execute only in the sequencer? The only way that I know of that allows us to execute the wait only inside the sequencer would be if we had 2 parallel loops. So if we were to put the sequencer in this loop and then put the robot drive code in a separate loop, then any wait would be restricted to just the sequencer and would not affect robot drive code. The challenge with this approach is then synchronization between any decisions that are being made in the loop containing the sequencer and any decisions being made in the robot drive code. So, for example, last year, a lot of things happened with the drivetrain that were directly, when we climbed, the climb sequencer actually took control of the drive base at different points in time. And at other points in time, the driver had control of the drive base. And so you do want to maintain that synchronization. And so this would be much more challenging to do if you had the teams. Does that answer your question, really? Chat window keeps disappearing. Yeah. Sorry, for whatever reason, my chat window keeps like minimizing itself. Okay, so what are some thoughts that you might have on how we can implement a weight without it blocking the rest of the code? And you don't have to answer in terms of actual LabVIEW code. You can answer just in terms of, in words, how might we do a weight without actually preventing the loop from looping?
We could use a case structure.
Okay, so using case structure is what we'll get to in terms of how we'll implement this approach. But how do we actually run a timer without having how do we actually avoid having to use this wait for block? I guess is the question.
Is it in the folder called time structures?
I don't know if they're already on that. Where is that one?
It was on your screen, on the right upper hand. Yeah, I know it was on your screen.
There could be an answer in there. I've never even used any of these. I have to look through these. First pass is that these would still involve blocking calls if we were to put them in a loop with a whole bunch of other stuff, but I'll have to look more. I've never actually played around. Good catch. Any other thoughts? So what did we do when we were creating timers? So who remembers when we were making timers where we would be able to press a button and then count the number of milliseconds since we pressed that button? So what we were doing in those cases were we would record the start time from the clock. And then we would constantly subtract the start time from the current time. And we would look at the amount of time that had passed. And so what we can do is create a timer just like that, where one of the events that happens is we start the timer, and then we don't move on the next event until the time since the timer has started exceeds a certain amount. But we can keep looping because the clock's going to keep running. So we can cycle around and continue doing all of our other operations while the timer's running. It's no longer a wait for, it's a check to see if the timer has exceeded that certain amount of time. Let's see, Amelia is having trouble with the audio. Is anyone else having trouble with the audio? Amelia is also having that problem. I sound like a robot. Okay, let me see if I can call in instead of using this audio, the laptop audio. 1 second.
Are people able to hear me now?
Yes.
Can you guys hear me now?
Yes, we can.
Is that better?
A little bit.
A little bit? Okay. Yeah, I'm not sure why there's any background noise. I don't have any background noise on my end that I can hear. I still can't get my chat window to show up properly. There we go. Okay. Okay. So let me know if you guys have any other trouble hearing me. Were there any questions on the idea of using a timer in order to avoid having a blocking call for a wait? Okay, so what I'm going to do now is show you, there's a lot of different ways to make non-blocking sequencers. I'm going to go ahead and show you guys an option that we've been using just because it's pretty effective and pretty simple, and sort of just like the standard approach that we've been taking. So let's see here. So the basis of our sequencers are case structures. And the advantage of using a case structure is that if I set it up to be a set of numeric cases, I can have as many different steps in my sequence as I want. So it'll default to having 2. It's very easy for me to go through and very quickly add more cases. So I can have as many steps as I want in my sequence. The next sort of key part of this is that we have to have memory of what step we were on what step we were on previously. We can use either a feedback node or a shift register. There can be some advantages or disadvantages to both of them, depending on how you want to be able to reinitialize the sequencer under different situations. Because it's a bit easier to control when the reinitialization occurs, I'm going to go ahead and use a feedback node instead of a shift register for today. So if I take a feedback node from the structures palette, what I'm going to do is the following. I'm going to initialize the step at step 0. The output of the feedback node will be the input to what step we're in. And then we're going to go ahead and run that out through the sequencer and back to the feedback node, so that we always maintain a memory of what step we're in. Now, the convenient part about this is that it's really easy for us to proceed to the next step. And so the way we do that is we take a select block, and when the select block is false, all we do is pass through the previous state. So if whatever Boolean value we put into the select block is false, we're going to stay on exactly the same step of our sequence as we were before. But if our trigger or whatever we have that's going into that whatever we have that should tell us to go to the next step is true, we're going to increment the step number by 1. And so, oops, excuse me. So basically this is our trigger to advance would get hooked up to the Boolean input on the select block. And then we would have this exact same structure in every single one of our cases. And the only thing that would change between the cases is what we use to trigger the select block. And the rest of the structure remains the same for all of the steps in the sequence, except for the last step, where theoretically you just wouldn't have an advanced structure. You would just freeze the sequencer at that last step, assuming that your sequencer doesn't reset. So like if this was a climb sequencer, you'd have it freeze here. For other sequencers, you may want to be able to reset the sequencer and go back to state 0. So that's a little bit, I guess I should say that is application dependent. So again, when we start out, we are in state 0. If our trigger is false, we stay in state 0, and so we come back around, and we're still in state 0. If our trigger is true, we're going to add 1 to 0, and so the next time we come back around, we're going to be in step 1. And then we're in step 1, and again, we're waiting for this trigger. When we're false, we stay in step 1, and then when we see that trigger again, we'll then advance to step 2. Does anyone have any questions about how we advance from one step to another step inside of the sequencer? Okay. So what I'm going to do is go ahead and just create a couple of dummy examples for actuators that we could be controlling. So I'll just call this piston number 1. And I'll call this piston number 2. Oh, it named it for me. Cool. Okay. So something that we might do is say that we've got a climb sequencer. But say we're writing the code to climb. Let me go ahead and put a loop around all of this so that we can actually watch stuff happen here. Okay. So one of the things that would be typical for us to do if we were doing a climb sequencer would be say that piston 1 is going to pull some sort of release pin that extends the climber, and piston number 2, maybe that engages or disengages a PTO at different times during climbing. And so if during normal robot operation, both of these are false, the very first thing that we might do in the sequencer is to go ahead and set both of them to true. So we pull the release pin on the mechanism, and we go ahead and shift our gearbox into low gear or into the PTO state. And so the way we would do that is we'll just have true constants. And I would recommend that when you're doing these sequencers, you label your constants so that you know what action they're performing. So I would go here to visible item and label and literally write down, this is pull, or I'll say retract release pin. And then this one I would call, I don't know, engage PTO. Now let's move this over here. And then throughout most of the climbing sequence, maybe we want to keep those values as true. Right? We want the pin to be released, and we want the PTO to be engaged. But maybe part of the step is that on the very last, the very last step is, for whatever reason, we've got to release the PTO in order to disengage the climbing mechanism. And so our very last step here would be to disengage the PTO and set that to false. And then the other thing I'm going to do real quick is I'm just going to create an indicator on the current step of the sequencer so that we can see what's happening. Step. Okay. A little more visible. And then I'm also going to just increase the delay time so we can see it goes through the steps on each loop cycle. And the other thing I'm going to do is make it so that we always advance to the next step. So I'm just going to quickly, for now, make it so that all of our triggers are set to true. And so we're going to immediately advance to the next step as soon as we go through it. Now, I'd also recommend, I should mention this, so if you go here and right-click and go to Visible Items and Subdiagram Label, you can turn on these text boxes up here in the subdiagram, and I would also add some sort of description as far as what step you're on, and maybe say what it does, so that when someone else comes along and looks at your code, they understand what you wrote. Okay, so if we run this, both of these lights should immediately go green, and then we should count through the different steps, and then hopefully at the end, I think piston number 2 should go dark again. Let's see if that happens. With green, we're on step 1, step 2, step 3, and then on step 4, the piston retracts. Are there any questions about how this sequencer works, how we are advancing between actions and how we are changing the states of things that we care about? Okay. So let's go ahead and take a look at how we might design a trigger that isn't just constantly always that isn't always true. So I'm sorry, just okay. So let's do the time one. This could also be a sensor value, so I'll show you how to do a sensor value as well. But let's do time first. Actually, let's do a sensor. Let's do time first, since we talked about time. So the first thing that we need to do is, if we're going to use a timer, so again, I guess I should say, there's nothing fundamentally stopping us from putting a wait for block in one of these case structures. If we did that, it would work, but again, we'd have the exact same problem as what we had in the flat sequence with this, where nothing else would happen until this wait was completed. And so the fact that we're using a case structure instead of a flat sequence doesn't absolve us of that problem. What's going to fix that problem for us is the following. So if we use a timer, we do have, the first thing that we have to do is we have to start the timer. And so what I'm going to do is you're going to place a timer block here, and I'm going to say that our first step is to engage, or I'm going to say retract release pin, engage PTO, and start the timer. So those are the three things that are happening in this step of the sequencer. So when we start the timer, we're going to record the time that we were at in this block. And we're going to need to have some memory of what that time is. So again, you could use either a shift register or a feedback node. I'm going to go ahead and just do another feedback node for consistency. And so now, the value that's coming in here is the, is the remembered time from when the timer was started. So from when we were last in step 0. So, and just for funsies here, although it shouldn't really matter, I'll go ahead and initialize the feedback node with a real value. Generally, sequencers are going to be set up such that you could not initialize this feedback node and nothing bad would happen, but just for completeness sake, I'll do that. Now on the next step, we can say, wait, what we're going to do on this operation, in this step, is wait for, we'll say, 5 seconds before proceeding. So what we can do is take another clock. We can do a subtraction from the time that we remembered, and then we can go into our comparison palette, get a greater than check, and if the difference between the current time and the time when the timer was started is greater than 5,000 milliseconds, then we will proceed on to on the step 2. So let me go ahead and make an indicator here again. So I'll call this timer value, just so people can see the countdown. And the other thing that we do need to do is we need to connect something to all of these tunnels that are open. So this is, again, a little bit application specific. For step number 1, what we want to do is maintain the memory of the previous value of the previous timer. We don't want to change it. So we're just going to directly pass through the previous time back to itself. So as long as we're in step 1, we're just going to keep the previous time remembered inside the feedback node. For the following cases, it's kind of up to you. You know, again, it's application specific. If you don't use another timer again, you could, it doesn't really matter. You could, you know, right click on this and type in 4265 and no one would care. Like nothing bad would happen. Generally, the practice that I'd recommend is that you connect that when you don't have anything specific to do, maintain the previous value. So just keep the time that we last saved in it. That way, if another coder comes back in later and wants to use the timer, it's a little bit more obvious what value is stored in the feedback node at any given point. So if we run it this time, we'll start on step 1, or step 1. We're waiting until we hit 5,000. Now we're on step 3, and now we retract that system. Does anyone have any questions on how that timer implementation works and how that triggered an advancement of the steps? Okay. So something that I just want to sort of show here is the fact that this is parallel. So I invent piston number 3, and I create a control. This is my, we'll call it Adam smashing the button here, that directly controls piston number 3. Let me make, so let me change that to a push button. Okay. So the point that I want to make is in states 0, 1, 0 and 1, we don't have any blocking calls. Now, in state 2, I'm going to put the blocking call that I keep warning you about in here so you can see what the effect is on how the robot is controlled. So if I put a wait here for 5,000 seconds, which is the same amount of time that we're waiting using the other method here, and we run this, while we're waiting for that, I can click and unclick this button and make piston 3 move. But now that we're in this other wait, I no longer have control over that piston. And then now that we're out of that wait, I do. And so while we've got that blocking call, you lose control of anything else that's happening in that same loop as your sequencer. And so that's why we want to avoid the blocking calls. Are there any questions about what I just showed? Okay. Let's see. So I'll just quickly show you, what it would look like with a sensor in one of these places, and then I'll move on to show you some real examples from this year's robot and last year's robot. So another common way to do a trigger is that we look for a sensor value. And so if I make another button that is, we'll say, elevator limit switch, this can be some sensor that we're always checking. And what we'll do is we won't advance to from step 2 to step 3 unless the sensor value is what we want it to be set to. So I'll just put that there. And so again, if we're running, we're in step 1, we're waiting for 5 seconds. And then we're going to stay stuck at step 2 until that sensor value is what we want. And then we'll proceed to step 3. Any questions on that or anything else that we've talked about so far before I go on to showing some examples? Okay. Again, the other thing about sequencers is this is also one of the more common questions that teams that are struggling with software tend to ask is, hey, we've got an arm that has to extend, the pistons have to extend in a certain order. Can you help us do that? So it's pretty quick to run over to another team and help them implement a sequencer like this on LabVIEW and get them running. So it's definitely a tool that is pretty fast to implement and can really help some other teams out. They often tend to struggle with these. Okay, so let me open up first the climb sequencer from this year, which is fairly simple. And then I'll open up the climb sequencer from last year, which is not very simple. Yeah. Okay. So we've got set up from this year is we have a master state controller, so it's a case structure, just like we talked about in the workshop on converting different button presses into different case numbers. And our cases are normal mode, which is what we spend the overwhelming majority of the time in. Then we have spin the control panel for rotation and spin the control panel for position, which we've never got around to implementing. And then the fourth case was, the fourth state that we could be in at any given time was climb mode. And when we entered climb mode, what happened is we then started with the climb sequencer. And so the very first thing that is happening in the climb sequencer is we're starting one of these timers. We're also setting the PTO to false and the the climber pin to false, the climber power to 0, and we are setting a flag saying that we're climbing. Here I've made the mistake, or I think we made this climber sequencer like the Tuesday before Little Rock, so there are no labels saying what they do. So right there's already a mistake. I don't have any sort of the labels saying what these different things are doing. One thing that we do have is each step has a string that describes what it's doing, and that string is actually getting sent to the dashboard. And so as we go through each one of the steps, the different message will appear on the dashboard, and that means that we can go back in time and look at the logs of what happened. Go back and look at the logs from the match and see if we got stuck on a certain part of the sequence, or if something happened at a certain step of the sequence. So we also try to sort of report that information. So after we start the climb sequence, the next step is, it looks like we go ahead and flip the piston on the PTO and the climber pin, and we still have the climber power set to 0. And then we use the timer that we started, and we go ahead and wait 500 milliseconds for the climber to deploy before advancing to the next step. And then on the last step, step 3, we, instead of giving it a 0 for the climber power, we give Adam the ability to use the one of the buttons on the joystick in order to control the climber power. And it just sits there in the final state until the end of the match. It doesn't go back. We do have a way on the outside of the sequencer that allows you to reset the climb sequencer without rebooting the robot. That's a bit of an improvement from how we were running it last year, where we had to reboot the robot every time we wanted to restart the climb sequencer. Are there any questions about how this sequencer worked, or what the reasoning was behind any of the decisions for the climb sequencer this year? Okay, so I will go ahead and go into last year's code. And I'm not going to go through in excruciating detail everything with the climb sequencer. I think that would bring back bad memories for Amelie. But we can go through at least an overview of the climb sequencer from last year. So let's see here. Okay. Okay, so last year was much more state heavy because we had an elevator and multiple positions to go to. And so we had a lot more different possible robot states. One of them was the climb state. Once you enter climb state, there were also 3 different climbs that we could do. We could do a level 2 climb, we could do a level 3 climb, and we could also do a level 3 buddy climb. And for each one of those different climbing options, we had to have different sequencers. And I'm going to go ahead and go through the level 3 not buddy climb sequencer because it's the simplest of all of them to explain. What we have on the right-hand side are all the different actuators that we have to control throughout the sequencer. And so these include the PTO, they include what power to apply to the elevator or what set point to apply to the elevator. They include all of the arm states, whether or not we are turning on the vacuum pump. It includes information that changes the behavior of the drivetrain. Really, the climber last year touched pretty much every single actuator on that robot simultaneously in order to make it work. So let me set us back here at the beginning. Okay, so just give you a heads up, there are 14 total steps in order to make the robot climb to level 3. And there are even more steps to make it to climb to level 2, which is a bit counterintuitive, but it's how the mechanics worked out. So one of the first things that's going on here is last year's elevator could toggle between manual control, where the driver had direct control over the power going to the elevator, and set point control, where there was a PID loop controlling the power going to the elevator. And at different points in time during the sequencer, it actually had a toggle back and forth between applying a certain amount of power based on the joystick values and using the PID. So the values that are sitting out here on the left-hand side are different set points that the elevator had to go to. And then you'll see at some different points inside the sequencer where we take the handover control directly to the driver and don't have the steps. So the very first thing that we had to do that year was release the mantis arms on the back. So we would pull a piston and they would spring down and be released. We're also going to start a timer. And then the next step is wait 250 milliseconds to make sure that the mantis arms have come all the way down and are fully extended. At this point, we've set a set point, the level 3 start set point of 62 inches for the elevator to reach. And we have some sensor readings here that are waiting for the elevator to reach that point and have been stable at that point for a certain amount of time. Once that's happened, we'll then proceed to step 3. This step, the pins for the mantis arms extend again to lock the mantis arms in place and keep them from ever folding back up into the robot while we're climbing. And we also start another timer. So there's something after this that also needs a timer. And so we have to start a new timer so we can measure the time off of this step versus some previous step. So the second timer is waiting 500 milliseconds for the pins on the piston to fully extend and grab onto the mantis arms. At this point, we're now waiting for the driver to give the climb command. So the manipulator started the climb sequencer, but all that technically does is raise the elevator and deploy the mantis arms and raise the elevator to a set point. The robot doesn't actually start climbing until the driver presses the trigger. And so here we're waiting for the driver to press the trigger before proceeding on to the next step. So this one was a bit of a challenge. This was the one to fix that Amelie and I had to write at Smoky Mountains last year, Thursday night. So there were some real challenges with getting the elevator to a consistent height so that it could deploy, so that it could engage the PTO in the gearbox when the elevator was at exactly the right height. And if the elevator wasn't at exactly the right height, the AM steel wouldn't have the correct length in order to pull down the climbing legs. And the PID on the elevator isn't good enough. It could sort of do plus or minus an inch on the accuracy of how high the elevator was. In order for the climb sequence to work, we needed closer to plus or minus a quarter of an inch accuracy. And so the solution that we came up with was the elevator actually raises to a higher height than is required. And then as the driver climbs, the elevator moves down very, very slowly. And as it moves down, it will pass the height at which we should engage the PTO. And so here we're checking to see whether or not, so we start out actually 2 inches above. As we pass the value, the height that we're supposed to be to engage the PTO, then we extend the piston. And we were able to get a much higher level of accuracy for the elevator height doing it this way. So once we pass the engagement height, we change the value on the PTO and engage the PTO. We then have another weight to ensure that the PTO is engaged and that everything is set up correctly. At this point, the driver is still climbing, and the robot is also driving forward or backwards onto the hab. And so what we're waiting for here is for the sensor on the bottom of the robot to detect that we're on the hab. And so we're not going to proceed to the next step until we pass that, until we see that we're on the hab and aren't hanging off the hab. You'll notice that we have a safety override here, so that if something happens to the sensor, they can override the sensor and still proceed to the next step. Let's see. There's also, the driver also has to manually confirm that the robot is on the hab before it proceeds. The next step is stop climbing. So this will shut off stop moving the elevator, I should say. Then you're going to go ahead and disengage the PTO so that the legs retract. We'll move the elevator, sort of bump the legs, so that the legs come all the way up, or at least part of the way up. And then the very last step is to turn off the elevator, and it'll stay on that very last step. So this sequencer doesn't really have a reset. It's going to stay at that last step for the rest of the match once you get there. Yeah, I mean, that's a lot. I don't, there's no reason to just sort of memorize what I just said, other than, really all I wanted to convey was the types of complicated actions that you can do with sequencers, and what kinds of triggers and wait fors you can have when you're designing how to move from one step to the other step in the sequencer. Does anyone have any questions about any of the stuff we've talked about with sequencers so far? Because after this, I'm going to go ahead and move on to autonomous. Okay, so Amelia asks, how did we do the sensor override? So to go back to that one, in order for us to go from step 9 to step 10, this value, the value in this line has to be true. And in order for it to be true, one of the buttons on the joystick had to be pressed, and these conditions had to be met. If we didn't have a safety override, we would have done this, where the button has to be pressed on the joystick, and the value from the sensor has to be true, saying that the robot is on the ground. What we have instead is the robot can be on the ground, or the master safety override can be engaged. So whether or not, so if you engage the safety override, you'll get a true at the output of this OR, whether or not the sensor is confirming that we're on the ground. Now we're still waiting for the human to hit confirm on the joystick, but it does override the sensor and allow you to proceed. Does that answer that question, Amelia? Awesome. Any other questions or comments on it? Okay, let me go ahead and I need to get some more water and I'll be right back.
Party time.
Okay, I'm back. Can everyone still hear me?
Yep.
Awesome. Okay. So we're going to go ahead and move on to autonomous. Although I want to mention one other thing that I keep forgetting to mention in every single workshop. So I just want to show real quick, and I just had it on the schedule today so we cover it, is a disable structure. So if anyone's familiar with text languages, you can comment out code. A disable structure is LabVIEW's equivalent to that. So if I've got some sort of operation here, I can go into structures and grab a diagram disable structure and place that around that. And this, anything that is inside of the diagram disable structure won't execute. The only sort of tricky thing is how do you get rid of it? If you click on it and delete it, you'll delete everything that's on the inside of your disable structure, which you probably don't want to do. So what you need to do is right click on it and say remove diagram disable structure, and then you're back to normal. I just keep forgetting to mention that each time. So any questions on how to sort of turn off different parts of your code with that? Okay, so let's take a look at autonomous stuff. So before we look at the actual code, why don't you guys talk for a bit about the different things that the autonomous code should be able to do? Like, what are the desires that you have for the capabilities of an autonomous mode? Alex, why don't you get everyone started?
Handball auto, I don't know.
Sorry, what was that?
I said 10 ball auto, but what was the question again? It was like,
So 10 ball auto is definitely a goal. I want to be a little bit more general than that. So the question was, what are the goals for the autonomous architecture? So let me give you an example of what a goal might be. So a goal might be, you don't want to have to duplicate code between your autonomous structure, your autonomous code, and your teleoperated code. So if you've got code that controls an elevator, you don't want to have to write it twice. So we'll call that goal 1. Avoid code duplication. So what might be some other goals that we might have like that? Sort of broad goals that would be true for any season.
my favorite, writing autonomous in the queue line with the easy, like, my block sort of things.
Okay, so create new autos in queue line. Okay. Actually, I guess that one has to be right.
A very fundamental goal is that our robot should also be able to follow an autonomous path, and associated with that is generating an autonomous path.
Okay, so robot should be able to follow, I'll say, a user-defined path. Okay, what else?
We should be able to call in different subsystems in a program.
Okay, so like access all robot subsystems in autonomous. Is that what you mean?
Yeah, so like we should be able to write a program that says when we shoot, it should be sequenced.
Okay, okay. What else?
Easy debugging.
Okay, easy debugging. So easy debugging, and I'll put in that and simulation of auto modes. That kind of also goes back to developing something in the queue, right? You want to be able to simulate it so you can test to make sure you didn't screw up. What else? Let me see if I've got any more on my list here. I think we hit most of them. Okay, so some other ones that I have on my list are clean restarts and aborts. So if something goes wrong and we have to stop the code early, it should transition in the teleoperated code without anything crazy happening. If we run an autonomous mode and then immediately want to run another autonomous mode while we're testing, it should be able to do that without us having to power cycle the robot or do anything else weird. You should be able to perform actions in parallel, and this is kind of a large one. Be able to perform actions in parallel. And what I mean by that one is, you know, if the robot is driving and we want to pre-spin the shooter, we don't want to have to wait until the robot is done driving before we don't want to have to say, send the drive command, wait for it to be done driving, and then send the pre-spin the shooter command. What we want to do is say, while you're driving, be pre-spinning the shooter. And so wherever possible, we want to be able to run stuff in, simultaneously, just like we would be able to in teleoperated code. In fact, that was one of the problems one of the challenges that we ran into at Little Rock was there was a need to do some things in parallel that was not anticipated. And the autonomous architecture that we developed didn't easily support doing those actions in parallel in that way. And so we sort of had to come up with kind of a janky fix in order to allow for that parallelization. As we get further into this, we can talk about specifically what caused that issue. And then I think there was one more. Oh, be able to select between multiple autonomous plays. That might seem simple, but it didn't used to be. It's back when I started in 2008, our very first year to select between autonomous plays, we literally had a bank of switches mounted to the side of the robot, and you had to flip the switches in a certain sequence in order to pick your play. And then that was a lot of weight, and so the next year we set with these little dip switches. There were little miniature banks of switches like you see as reset buttons and stuff, and you had to use a hairpin and set a binary code on the dip switches for each match. And so, you know, if you had 30-something autonomous plays, you'd have a playbook, and you'd flip through the playbook and look at the binary number you had to type in by pressing the switches, and that's how you selected your autonomous modes. Now that you have a computer that's hooked up to the robot and you can select them with a drop down, it's a little bit nicer. But it was, people had some interesting approaches. I've also seen Mars in 2012 selected autonomous modes by, you could put the balls in the magazine, and there were sensors for each of the positions in the magazine, and they would put the balls in a certain order in the magazine in order to select the autonomous mode. So teams came with all sorts of weird solutions before dashboard code came along like we have now. Any other goals that we should have for autonomous, or any other thoughts or questions before we go on? Okay. So, I mean, these are sort of the goals that we had at the beginning of, so for those of you who don't know, last year we didn't have any sort of autonomous capability. We ran teleoperated code in autonomous and didn't have any sort of architecture to support this. The default first architecture does not have almost any of these capabilities. It can select multiple autonomous plays, but in terms of what's built into the code, it doesn't really meet any of these other goals. And so our big project for the summer, in addition to the Swerve drive, was developing an architecture that allowed us to achieve these. And the sort of the overarching goal that we had was, back in 2014 was one of the few years that you could play defense during autonomous. And during the finals on Einstein, I believe it was Symbiotics and Cheesy Proofs, we're coding new autonomous plays in the queuing line in order to fight against each other and actually do autonomous battles where one would try to block the other one from scoring. And we wanted to develop an architecture that would allow us to do that kind of autonomous competition whenever we get to that level. And so that was sort of our overarching goal with that. And I don't know that we're quite there, but we got pretty close. I mean, we did that 5-ball auto that we had in Little Rock was written in the queuing line at Little Rock at different points in time. So
it scared the people next to us.
Say it again.
It scared the people next to us.
Did it really?
Yeah, when we tested like the auto like test mode and like it went the people next to us, I think they were from Mexico. One of them like jumped and screamed. It was funny.
Well, hopefully you then showed them what it did and they thought it was cool. So, okay. So in order to understand the autonomous architecture, we're going to have to do some stuff first. We're going to have to talk some about the overall code architecture that we've been using for this year that we developed in the summer. And we'll talk about sequencers again. And then we'll also be talking about how to work with files and strings and some other things, fundamental LabVIEW things that we haven't hit yet, but are really important to how we build autonomous plays. And I don't know how far we'll get tonight. We'll probably get maybe to the sequencers, and that's probably where we'll pause until Thursday. So what I'm going to do is open up this year's robot project. And one of the things that I sort of want to show is that autonomous is pretty close to, when you add autonomous code, it pretty close to doubles the amount of code that you have to write, at least. So, for example, if I open up all of these folders, that is, all these functions here are all of the functions that are required to make the robot move. And so I'll remove sensors from this. So all of this is everything that's required to make the robot move, not including sensors in TeleOp. In order to run even the pretty simple autonomous modes that we had, all of these functions are also needed in order to, of those functions, and then most of these ones are also autonomous. All of these functions are needed in order to execute the autonomous modes. And that's even with us achieving the goal of not having to duplicate any of the teleoperated code. So it does sort of, and those ones too, it does sort of explode the amount of code that you end up having to write. So it's just something to keep in mind in terms of the overall complexity. So our code fits into the architecture that first provides teams, but it also bypasses pretty large sections of it and does it our own way. So we still have a begin VI, just like we showed in the workshop where we were talking about the first architecture, where we do all of our initialization. So you know, we've got the initializations for all of the motors on the drivetrain. We're storing our reference information in the global variable so they're accessible elsewhere, just like we saw in those examples. So all of that's pretty similar. We have packaged all of our initializations into sub-VIs just so that the code's a little bit cleaner, so you can look at the initializations per subsection, subsystem. We have done a couple of things where a few of our initializations do have to happen in order, and so that's why they're in a sequence. So some of the constants have to be initialized first. So for instance, what drivers are available, what states exist, that kind of stuff, and actually what position the robot's starting at, those all have to be initialized before we get to any of the motor initializations. And then because of the way the IMU is hooked into the control system, the motors have to be initialized before we initialize the sensors. And so we have a little bit more structure for initialization than the first default. The next thing that's happening is we don't touch the autonomous enabled, well, maybe a little more specific. In this, okay, let's see how I do this. So these VIs over here that look kind of funny, that have the little arrow, little curvy arrow, those are VI references. So there are multiple ways to call a block of code in LabVIEW. The way that we've been working with calling the code in LabVIEW is you take the sub VI, like this one right here, and you place it on the block diagram. And when you loop around, you execute whatever's inside of that block. Another way that you can do it is with a VI reference. So instead of this being a block like this one, this is you can almost think of like a file name for the block that you want to call. And so in first architecture, they would have you put your code into a block and put its file name here. And then that file name would get called by the start stop VI here during autonomous. And I'm going to talk more. It's okay if you don't understand how the reference VIs work. We're going to talk more about that later on because we also use those in autonomous, but I'm going to skip over that for a little bit. What we have done is in their autonomous code, they have some baseline code that moves the robot forward. We've deleted it. So the only piece of first autonomous code that we're running is basically this update block that tells the field management system that we're in autonomous mode. So we've cut everything else out except for the reporting that says, hey, we're running autonomous right now, just confirming with you. In TeleOp enabled, usually like the default first code has all of your drive code placed inside of this case structure. We took all that out. So the only thing that's happening in TeleOp enabled is that we're reporting to the driver station that, hey, we're in TeleOp enabled right now. No changes to how we handle when the robot's disabled. We don't want to mess with that. Same, no changes to how we handle it when we're disabled in autonomous mode or when we are disconnected from the field. And then our finishing operation is the same as normal first code. So we take our motor references and we go ahead and close out all of our actuators and sensors when we get to finish. We've also removed the first camera code from here. There's some code that looks for USB cameras. We don't use USB cameras going through the Rio, and so we've removed that to save processing time. We've left the server code that's running the communication between the driver station and the robot. We haven't touched that. And then pretty much everything that we do is placed inside of periodic tasks as a block that runs in parallel. And we should probably think next year about how to clean it up a little bit more. But pretty much all of our code is stuffed into periodic tasks. Are there any questions about what you've seen so far, architecture-wise? Okay. So what I'm going to do is I'm going to start with how the robot operates and teleoperated, and then talk about how it interacts with sensors, how it makes decisions, how it interacts with sensors, how it interacts with actuators, how it communicates with the driver station. And then I'll show how we interface with autonomous instead of teleoperated control. So we have one master control loop that is running in periodic tasks that is handling all of the decision making for the robot. Some teams like Mars run separate control loops. So, each subsystem will run in parallel. So, their shooter and their control panel spinner or their climber will all have separate control loops. There are some advantages to that, but I think that overall there's more disadvantages. Namely, it becomes difficult to synchronize between the parallel loops. And so, because sometimes decisions made in one loop can interfere with a decision made in another loop. In most cases, that's not a problem, but it tends to be like if you've got a very complicated climber like we had last year, for example, that has to interact simultaneously with every single subsystem on the robot, having separate control loops can be a problem. So we've chosen to run a single control loop. The challenge with running the single control loop is that you then have to be very careful about how much computation time all of your operations and decisions require. If your decisions require a lot of computation time, you risk slowing down the entire control loop and introduce lag between the driver and their ability to control the robot. And so you do just have to be very careful about making sure that your code runs quickly, at least any of the code that's running in the control loop. So we do have a flat sequence inside of our control loop. It's only got 2 frames. So the very first thing that does happen inside of the control loop is we get what we call instructions from the driver station. Those instructions are all of the joystick values and buttons from the driver joystick, all the joystick values and buttons from the manipulator's joystick, as well as any buttons that they have on their tablet. One of the things, and so one of the other things that we do in our architecture is we have a global variable dedicated to driver station instructions. And so anywhere in the code that you want to use, say, the Y button from the driver joystick or the right Y-axis joystick, you can just drag and drop the global variable for that and pull out that value and use it anywhere in the code. So that way people aren't constantly risking accidentally selecting the wrong value out of the array or doing anything else. It's always a very consistent way to access those values and prevent those kinds of bugs. Once we get all of those values from the joysticks and from the tablet, now we actually run all of the decision-making code. You'll often hear us refer to those as state controllers. And so generally, we have a master state controller, which might control or influence multiple subsystems. And then there will be state controllers for each individual subsystem. And then there may be some things that happen at the end that change their behavior based on what happened in the other state controller. So what we've got here is, this is like the code that we wrote before that converts the multiple button presses into a state name. Excuse me. My throat's starting to die here. And so this is actually just a stock VI that you can drag and drop in here. You don't have to create this new every time. Then you have the master state controller, which we showed earlier today, which just has the options of normal mode, position and rotation control for the spinner, which aren't implemented, and then climb mode. And because these different states could influence how all the multiple subsystems work, those kinds of decisions are made together in the master state controller. Then we have state controllers for each of the subsystems. So we've got this is the limelight, so you can actually change things like whether or not the LEDs are on or off on the limelight. That goes in here. This is everything that happens with the shooter, everything that happens with the intake, everything that happens with the swerve drive, and everything happens with the turret. And this is currently unfinished. Because the different things, because different actions in each of these subsystems could change what color we want our LEDs to be on the robot, the LEDs come last. The pink lines that are connecting all of them are actually not used for anything right now. They're only there in order to either share state information between the blocks, which I can't remember if we actually use that feature or not. But more importantly, they're being used to maintain the sequence. So because the data have to flow from left to right along the data line, I make sure that you execute this block, the select block first, and then the master state controller, and then all of the subsystem state controllers, and then the LED state controller. We could have implemented this exact same approach with another set of subsystem frames, like another set of these sequencer frames, but that would have been equally valid. As we just happened to choose using this method because we thought it would look a little bit cleaner. And then there are some decisions that can sort of be made what we call asynchronously. So there's not a huge, they're sort of non-critical functions that don't have to occur synchronized with anything else. And the only thing that we have this year that falls in that category is the state controller that manages whether or not we're in power saving mode on the robot. It doesn't really matter if that's synchronized with other stuff. So it's just floating off there on the side and not connected to anything else. Are there any questions with this flow from getting the instructions from the driver station to running that information through the master state controller and then the subsystem state controllers?
I have to go because I have some jobs to do, so I'll see you guys later.
Okay, see you, Dominic. Any questions or comments before I move on? Okay, so running and just to give you a baseline, we try to keep our control loop running at around 30 milliseconds. If it's much slower than 30 milliseconds, the driver is going to start to notice some lag between their commands and what the robot's actually doing. So running in parallel to the control loop are a lot of other loops. So we've got 2 loops here that handle data from the driver station. So in this block, which is inside the control loop, we're getting instructions from the driver station. In the parallel loop, we're getting data from the driver station. And the distinction here is a little bit vague, like it's a little bit of a not clear boundary. But what it comes down to is driver station instructions are things that we're going to mimic in autonomous mode, and driver station data are things that we're not going to mimic in autonomous mode. And you'll see at the end of the night where that mimicking comes into play. But the way I would look at it right now is driver station instructions are things that let you drive and directly control the robot, whereas driver station data might be things like whether or not you're in super test mode, or whether or not your safeties are over, like any of your safety overrides, what driver profile selected, sort of your settings and your configuration information, and not your driver controls. Are there any questions about, or like any questions about the differentiation between what we call instructions coming from the driver station and data coming from the driver station? Okay. So the next parallel loop that we have is for sending data to the driver station. So if we go into this block, there is a lot of stuff here. And this is where we send all of our sensor values from the robot to the driver station. So all of the indicator lights, all of the, the azimuth failure warnings, all of that kind of information gets sent in this block, running in parallel with everything else. The next 3 blocks are sensor blocks that are running in parallel. In the low priority sensor block, we're only running this loop once every 500 milliseconds. So we only run this loop once every, or twice a second. So the sensors that we put in here can't be critical for how we control the robot or how we get feedback. But we don't want to run all of the sensors at really high data rates because we're trying to conserve the bandwidth that we have available on the robot and on the CPU for doing actions that we really care about. So some of the things that we're getting in low priority sensors are, let me see here. Oh, not a whole bunch actually anymore. Oh yeah, okay. We're getting information on the pressure transducer. So whether or not we're pressurized, we don't need to know that, more than 2 times a second. We're getting information about whether the compressor is turned on or off. And then inside of this block, which is actuator faults, we're getting all the information for whether or not any of the motors are overheating, or whether or not, oh, that's an interesting thought. Or whether or not we have an azimuth failure. And actually, now that I say this out loud, we may want to move the azimuth failure to a higher priority call. That may be why sometimes we get, that may be driving some of the false azimuth failure warnings that we're getting on the encoders. So we can put that down as something we should look at. If we're pulling them pretty infrequently, that could actually be causing some squirrely issues. So, but we would certainly still leave the temperature readings in the low priority sensors. We really don't need to know really often what the temperatures are in each of the motors. And then in, I'll skip to high priority sensors, which are running 20 milliseconds. So we're running high priority sensors, we're running that 50 times per second. And if you look in there, that sensor's like all of the encoders on the shooter wheels, the encoders on encoders on the shooter wheels, the velocities of the wheel speeds, the potentiometers on the azimuth encoders on those sort of modules, and then information about the turret, which is not fully implemented, about the turret encoder. In the other one that's sort of running in parallel here is Get Vision. This is handling all of the information coming from the limelight, and it's also doing a number of the calculations for the sensor fusion between the limelight estimation of distance and the robot's estimated distance based on its estimated position on the field that we talked about. If we were to put, if we were to get the LiDAR system sensor fusion up and running, it would probably also go in this block. We might want to rename it from Get Vision to Get Vision and Get LiDAR or something. But in order to maintain synchronization, we would probably place the LiDAR code inside this block as well. Are there any questions about these 3 sensor blocks so far? Okay. The other block that's running in parallel here is also sensor related. This one is pose calculation. So this is all of the math and all of the sensor readings required in order to estimate the robot's location on the field. So because those sensors need to be synchronized with each other, they're being handled in the same block. There are some nuances with the fact that this is not synchronized with the limelight, so there are some challenges there, which could cause issues in edge cases. I don't know that we've seen that problem occur, but it is possible. So the synchronized sensors that we have in this block are all of the wheel encoders and the IMU as well, all the IMU readings. And the outputs of these blocks are the robot's X, Y, and angular position on the field at any given point in time. And those values are used both in autonomous and during teleoperated. I'm going to skip that loop for a second. Are there any questions before I move off of sensors and sending and receiving data? Okay, so what we try to do is basically keep all the sensors and data loops above the control loop. And then below the control loop, we have the some other parallel loops, typically one for each subsystem that directly interfaces with the actuators. It's really critical that the actuator commands, the interface between LabVIEW and the actuators occur in loops that are not, occur in a loop that is different than your control loop. The reason for that is sending a command to the CAN bus takes a long time. Now they've made some modifications to the CAN bus this year that qualitatively seems to have dramatically improved it. I haven't measured it since we got the new code this year to see what the advantage is. But in last year's code, like with last year's LabVIEW version, sending a command to a motor might take 20 or 40 milliseconds. And so if you're trying to maintain your loop time, your control loop times at 30 milliseconds, and you need to update 4 motors, depending on how you do that, that might take hundreds of milliseconds. And so you could basically lock up your robot for the entire time that you're trying to send those update commands and prevent you from doing anything else. So that's why we split things up into separate loops, and we split up subsystems so that any commands that are being sent for a given subsystem are synchronized, but sending the commands for one subsystem will have not a significant impact on the lag for a different subsystem. So we've got the drivetrain speed motor, so the motors that are spinning the wheels on the drivetrain, that's one subsystem. One thing I'd like to point out is basically the output of all of the state controllers are global variables that are these global variables that are sort of the very last, raw value that you are going to send to the actuator. So you should put very little decision making inside of this subsystem, inside of the subsystem actuator loops. So the state controllers here in the main control loop, they should decide what power from -1 to 1 you're going to apply to the motor. And pretty much the only thing that should happen in these parallel loops is to send that determined power to the motor. Now, this year we've added some extra things that do happen in these parallel loops. So we've added some safety interlocks to these loops because it's easier to manage them there. And so you see if there's a failure on one of the modules, we're going to cut off power to the drive wheels. And then the other thing that you see is for every single actuator here, you're going to see this test actuator block that Amelie wrote. So what this block does is allow us to override the state controllers and directly control each individual actuator from the dashboard. So this year, a lot of the actuators are connected, so and automated. So when we spin up the chute, when we try to shoot, the azimuth motors move, all 4 of those. The drive motors, all 4 of those move. The shooter wheels move, and so that's 10 motors move, plus the kicker and the V-belt, and the intake. So when we go to shoot, 13 motors move, and 1, 2, at least 2, 3 pistons fire. So, and all of it's happening automatically. So if you've got a, so we quickly ran into was a problem where when we were trying to test things, it was very difficult to test individual components because the whole robot would start to move and do different operations. And so we had to come up with a way to be able to bypass all of the other state controllers and just test individual actuators. We can make sure things were wired correctly, make sure that things mechanically were working the way that we were expecting. And so we're using these sort of interlocks here as the system. The advantage of doing it this way is because the testing interlock is the very last thing before the motor commands. You can be 100% certain that you have overridden all of the autonomous parts. Like there's no way for some sort of automated action to get to any of your actuators if you're in test mode. It'd be very hard to make a code bug where that would happen. And so it's a very safe way to do it. It bypasses the first test code, which is supposed to be in this test disabled, test enabled block. And we are bypassing their way of doing it and doing it our way for this sort of added safety reason that we've got here. So the other subsystems that we have are, we've also split up the Azimuth controller, the Azimuth modules. One thing I will note here is that for some of the PID loops, so last year the PID loop for the elevator was running in the master state controller, which was fine. This year we have a lot more PID loops, and it's a little bit more important that they stay synchronized, just because we need a faster response rate than we did on the elevator. And so for some of the actuators, we placed the PID controller inside of the subsystem loop as opposed to inside the state controller loop. This is the control loop for the turret, which is also not finished. The control loop for the shooter, which includes both the shooter wheels, the kicker wheel, and the piston on the cowl. So again, trying to keep things for a specific subsystem together. Intake and the magazine. So yeah, the intake, the flapper, and the V-belt. Items that are specific to only the climber. The kicker motor is still going to be controlled in the shooter even when we're climbing, but all of the pistons used for the climber are in the climber loop, the compressor, and the LEDs. And one of the other things you might notice is things like the LEDs are only running once every 100 milliseconds, whereas the Azimuth motors on the wheels are running once every 20 milliseconds. So again, we're prioritizing time-wise which subsystems need to respond faster in order to balance the load on the RoboRio and how much of its CPU that we're using at any given time. Are there any questions with the subsystem, the subsystem controllers and the actuator control loops before I move on? Okay. So I'm going to scroll back up to the control loop now, and we've got a case structure here. So when we're in TeleOp enabled, it's just what I described, where we get data, we get instructions from the driver station. The other options that we have are TeleOp disabled. Here it's very similar to TeleOp enabled, except that we won't get instructions from the driver station unless we're in super test mode. Now, so if we're not in super test mode, there will be no commands. No commands will get passed from the joysticks to the state controllers on the robot. If we're in super test mode, we'll be able to pass commands to the state controllers, and we'll be able to observe how the code reacts. Now, first code at a lower level is still disabling all of the actuators. So even though we're in super test mode, the robot's not going to move. That is safely hidden away from us, and we don't have access to change that, fortunately. At least not easily. Some teams can override that, but we don't have easy access to that. The reason that we then don't just keep, the reason why we have super test mode instead of just, basically duplicating the code and only having and always reading the instructions during disabled mode, is we don't want the drivers to accidentally enter a state or perform an action. So, theoretically, if the robot was already turned on and the robot was disabled and the driver pressed the auto targeting button, then when the robot was enabled, it would immediately go into auto targeting mode, which may not be a feature that you want. And so to prevent those kinds of situations from occurring, we have to go into super test mode in order to get those commands passed through while the robot is disabled. Let's see. Autonomous disabled looks exactly the same as TeleOp disabled. In finish and in disconnected and all of those, we just don't allow any commands to get sent to the state controller. We're defaulting back to the first code that's in these blocks anyways in those cases. So we just don't run our controllers at all, which does mean that you should never put our robot into the test mode that shows up on the driver station, like on the first has a little selector for you. Do you want to put your robot in test mode? Our robot should never do that. If you want to put our robot in test mode, there's an option on the dashboard on the upper half of the screen to put it into our version of test mode. So those are all of the cases except for autonomous. Are there any questions about this case structure before I show you what the autonomous case structure looks like? Okay, so this will be the last thing I talk about tonight. I'm just going to show you guys autonomous. So it's kind of messy because we kind of built on top of it throughout the summer. Didn't have too much time to clean things up. But this is what is generating the commands in autonomous. So in TeleOp, you have this block that is getting instructions from the driver station. In autonomous, you have a whole bunch of code, and the output of that code is to spoof the driver controls. So you're going to, inside of this code, pretend to move the joystick forward or backwards, or pretend to hit the button that fires the shooter, or pretend to hit the button that deploys or retracts the intake. The advantage of this is that if by following this pattern, we have immediate access to all of the TeleOp code that we've written. All we have to do is come up with code that mimics what the driver would do. And so that simplifies the code a lot and allows us to do new features pretty quickly. The disadvantage is the one that we ran into at Little Rock, which is it's not trivial for us to do things in autonomous that the driver can't do in teleoperated. So I think the ask from Dr. B was to deploy the intake, like cycle deploying the intake in and out while you're shooting. And while we can both deploy an intake and shoot, there isn't a good way, there isn't an automated way there isn't a way in teleoperated where it automatically lowers and raises the intake while you're shooting. And so there were some complications, which we can talk more about as we go through this, with integrating that functionality into autonomous. Okay, now the way autonomous works is there's a case structure at the beginning that handles initialization. So when you first start autonomous mode, things start up. So that will be where it checks to see which autonomous play it's supposed to be using. It will read out what kinds of instructions are going to come with that autonomous play. It's going to, apparently we don't need to do anything here, but if we did need to set any actuators to a default state, at the very beginning, we would put it in the auto init operation. We're going to start some timers, and we're going to set everything back to step 0 of autonomous mode. And then when we're in, after we enter auto mode, we stay locked with all of the values that were initialized. So we don't make any changes here once we're running auto mode. Now, the next thing that we have here is 2 sequencers that are running in parallel. So we have the mobility sequencer and the subsystem sequencer. The intention here was that, in general, the 2 things that you need to do in parallel are drive and press buttons on the joystick. And so as long as we maintain that level of parallelism, we'll duplicate what the driver can do. Now, the problem that we kind of ran into, again, with dropping the intake automatically, was there was a desire to do 2 different subsystem actions simultaneously in parallel. And we don't have support for that right now. We don't have easy support for that. So we can't do 2 different subsystems. We can't press 2 buttons at exactly the same time with a subsystem, but we could move a driver joystick and press a button at exactly the same time in the autonomous architecture. And then the last set of things here is for reporting. So it'll report any errors that we're having during autonomous, and also report to the driver station what step we're on in both the mobility sequencer that's driving the robot and the subsystem sequencer that is controlling the different subsystems. And what we'll start with on Thursday is talking about how the mobility sequencer works and how the subsystem sequencer works. And hopefully we'll also get into how we design the autonomous modes, like how we, from a code standpoint, so not an operational standpoint, how we write the autonomous modes, but how does the code read into different steps and convert those into a sequence of operations that it's going to go through. We're at